Welcome to The Explainer. Today, we're going to uncover the hidden science behind, believe it or not, concrete. Yeah, I know. It's the foundation of pretty much everything, but its incredible strength comes from a chemical process that's completely invisible. So how in the world do we figure out what's going on?
I mean, think about it. It's a question that feels a little bit like magic, right? You take this gray powder, you mix it with some sand and water, and poof, in just a few hours, it turns into a material so strong you can build entire cities with it. How does that transformation actually happen? What is going on inside that gray sludge? And we're not talking about some niche material here. The scale of this stuff is just mind-blowing. Look around you. Concrete is literally everywhere. Over half of everything humans make, by volume, is a cement-based material. It is, without any exaggeration, the bedrock of our world. So yeah, understanding it is kind of a big deal. So the secret, the magic, is a chemical reaction called hydration. This is where tiny cement particles react with water, and they grow these intricate, interlocking crystals that create incredible strength. But here's the catch. It's all happening on a microscopic level. It's a totally invisible engine of power. So how do you study a process you can't even see? Well, it turns out you can listen to it. Not with your ears, obviously, but by measuring the one thing that pretty much every chemical reaction gives off: heat. The technique is called calorimetry, and all it really is the science of measuring heat. So if hydration is the engine that's turning wet concrete into solid rock, calorimetry is like popping the hood and putting a sensor on that engine to see how hot it's running and for how long. Honestly, the best way to think about it is like a heart monitor, an EKG for concrete. The heat signature it picks up is the reaction's vital sign. It's the heartbeat that tells us exactly what's going on second by second as that material comes to life. And this is the gadget that lets us listening. It's called an isothermal calorimeter, and it is incredibly sensitive. You just put a tiny little sample of the wet cement paste inside, and as that engine of hydration starts to fire up, this device measures the teeny-tiny amount of heat it gives off. It tracks that heat flow with amazing precision. And what we get is the concrete's EKG. On the left, that spiky curve, that's like the speedometer. It tells us the rate of the reaction, how fast it's going. And that smooth rising curve on the right, that's like the odometer. It tells us the total heat released, showing us how far along the reaction is. Put them together, and you have the whole story. Now, we can break that story down into 4 distinct acts. First, the moment water touches cement, you get this big initial burst of heat. Then, strangely, it all goes quiet. That's the induction or dormant period. And that part's absolutely crucial. It gives workers time to actually pour and place the concrete. After that, it's the main event, the acceleration, where all the strength starts to build. And finally, things slow down in the deceleration period as the reaction winds down.
Okay, so we can see the reaction's heartbeat. That's really cool science. But so what? What can we actually do with this information? Well, let's take a look at how this awesome tool is used to solve some major real-world construction problems. Let's start with a big problem. I mean, a really big problem. Imagine you're building something enormous, like the Hoover Dam. You've got this unbelievable volume of concrete all curing, all hydrating at the exact same time. All that chemistry generates a tremendous amount of heat. And if the inside of that dam gets way hotter than the outside surface, that stress can cause it to literally crack itself apart from the inside out. Disaster. This is where calorimetry is a total lifesaver. It lets engineers test different cement recipes to find special low heat versions that react slower, keeping the temperature under control and preventing that kind of failure. All right, here's another headache. Modern concrete isn't just cement, sand, and water. We often throw in chemical additives or admixtures to give it special abilities. But what happens when those chemicals just don't get along? These admixtures are like superpowers for concrete. They can make it flow like water, set up in minutes, or even survive a deep freeze. They are incredibly useful. But pick the wrong combination of cement and admixture, and you can ruin an entire truckload of concrete. And that is a very, very expensive mistake. And calorimetry shows us the problem in plain sight. Check this out. The top curve is a beautiful, healthy reaction. That's our hero. But look at the bottom curve. With the wrong chemical, the reaction just goes haywire. It causes what's called a flash set. The concrete hardens almost instantly, and it never gets a chance to do the main reaction that gives it strength. It's a total failure. Calorimetry lets us catch this in the lab, long before it ever becomes a problem on a job site.
Okay, and this brings us to one of the biggest challenges of our time: sustainability. Making cement has a pretty hefty carbon footprint. So, the big question is, can we make concrete more environmentally friendly?
Well, one of the most promising ideas is to replace some of that cement with industrial byproducts like fly ash from power plants. They're called supplementary cementitious materials, or SCMs. But here's the catch. You have to be absolutely positive that these recycled materials are actually pulling their weight, that they're really participating in the chemical reaction and making the concrete stronger. And you guessed it, calorimetry gives us the proof. It's the smoking gun. This chart shows the heat given off by different mixes. You see that when we add stuff like fly ash or slag, the total heat is actually higher than with cement alone. That extra heat is the definitive signature that these SCMs aren't just sitting there. They are chemically reacting and contributing. This lets us design concrete that's both stronger and greener. It's a win-win. So, when we pull back and look at the big picture, what does this all add up to? It's about so much more than just looking at squiggly lines on a graph. It's really about designing the very future of how we build. It really boils down to this. Isothermal calorimetry gives us a secret window into that invisible reaction. And with that knowledge, we can engineer materials that are just fundamentally better, stronger, safer for those massive projects, and way more sustainable for our planet. By learning how to read these heat signatures, we've gone from just sort of using concrete to truly engineering it. It's like we've gone from being cooks following an old family recipe to being master chefs, writing brand new, precise chemical recipes for any job we can imagine. And that kind of leaves you with one last thought. We learned how to understand the strength of our entire civilization just by listening to its faintest thermal heartbeat. It really makes you wonder, doesn't it? What other invisible forces are all around us, shaping our world in these profound ways, just waiting for us to find the right tool to finally see them?